All right, let's talk about example 2. Here it asks us which of the functions listed below are examples of polynomials. So the first one, f of x is equal to x cubed minus x plus 4. This is in fact a polynomial. The next example, g of x equals x plus 1 over 4x, is not a polynomial because it has that fraction bar there. So that's not good. The next one, h of x equals 1 plus the square root of x, that looks like it could possibly be a polynomial. However, with the x, because we're taking a square root there, that is not a polynomial. All right, the next one, that one is very close to being a polynomial. However, all of the exponents we said earlier have to be integers. But if you look here, the exponent there is 2/3, which is not an integer because it's not a whole number. So this is not an example of a polynomial. The next one is a linear function. We just have n of x equals 5x. And if it helps you, you could put a little +0 there for the b value. But this is an example of a polynomial. We said earlier that all linear functions are also polynomials. So I'm going to go ahead and circle that one. So only the first one and the last one are examples of polynomials. All right, so that's all I wanted to say about polynomials. Now we're going to talk about another function called the reciprocal function. So in mathematics, the reciprocal function is known as f of x equals 1 over x. Now let's graph that below here. And I think what would be helpful is if we made a little table. So I'm going to plug in 1, 5, 10, -1, -5, and -10. So if I plug in 1, then my output is 1. If I plug in 5, then my output is 1/5, which is equivalent to 0.2. If I plug in 10, my output is 1/10, so that's equivalent to 0.1. And notice that if I plug in the same negative values, they're going to give me the same outputs, just being negative though. All right, now I have a question for you. What if I plugged in 0? Then our output would be 1 divided by 0. However, it is very likely that if you've taken a math class before, you will have heard that you cannot divide by 0, and we say that this is undefined. Now, if you are curious about why you cannot divide by 0, I've uploaded a really cool short video that explains why you can't divide by 0 on Canvas in a really digestible way. So if you're very curious about that, go ahead and hop on over to Canvas and watch that video. Otherwise, let's get back to graphing this. So here's my xy plane. So here's my x-axis, and we can call this either f of x or y. Maybe I should come back here and call this f of x, actually. So here's 1, here's -1, here's 1, here's -1. And if I plug in +1, then my output is +1. If I plug in -1, then my output is -1. And if I plug in 5, let's see, I didn't draw this very well. I will. All right, so if I plugged in -5, then my output would be -0.2, which we could say is like about right there. And if I plugged in -10, then my output is about right there. And so what you'll find is as you plug in those numbers going towards -infinity, the graph gets closer and closer to the x-axis. So it's going to look something like that. And as you plug in numbers between 0 and -1, then it'll be a very large negative number like that. Same thing, maybe you can see it here. If I plugged in 1/10, then, and the reason this is called the reciprocal function is because we take the reciprocal of the input and then that's our output. So the reciprocal of 1/10 is +10. And so let me just plot some points here. It's going to look something like that. And as I plug in numbers between 0 and 1 that get closer to 0, our graph is going to approach infinity. All right, now that's pretty much what I wanted to say about the reciprocal function. The next thing that we're going to talk about is what is called a rational function. And the reciprocal function is an example of a rational function. A rational function is just of the form f of x over g of x, where g of x cannot be 0, and f of x and g of x are both polynomials. So kind of just to restate that slightly differently, a rational function is when you take two polynomials and you divide them. The domain of a rational function is the set of all real numbers for which g of x cannot equal 0. So going back to this example, if I wanted to talk about the domain is always, for rational functions, everything that is not going to make the denominator 0. In this specific example, the only thing that's going to make the denominator 0 is if we plug in 0 itself. Therefore, when we're writing the domain in interval notation, we would basically say that it's everything except for 0. That's how you would write it as a sentence, but in interval notation, that would look like this. So -infinity to 0, union 0 to infinity. All right, and again, let me just write that as a sentence. We could say like everything except x equals 0. Okay, so let's come back down here. There are these things called asymptotes, and a vertical asymptotes are vertical lines that our function's graph cannot intersect or cross. For the reciprocal function, our vertical asymptote would be the vertical line x equals 0. For rational functions, vertical asymptotes occur when and where the function is undefined. So you'll often find when I am drawing vertical asymptotes, I use like a dashed line to represent an asymptote. And notice there's one right here along the y-axis because our function gets really, really close to it, but it does not intersect it. Okay. Now, you're also going to find something called a horizontal asymptote. And in this example, our horizontal asymptote happens to be the x-axis. So there are asymptotes on both the x and y-axis in this specific example. Now that's not always going to be the case. So let's see if we can see some other examples. Okay, and one thing to note about horizontal asymptotes is that there are 3 cases to consider when you are trying to figure out if there is a horizontal asymptote for a specific rational function. The first case is if the degree of the numerator is larger than the degree of the denominator, then there is no horizontal asymptote. The second case, if the degree of the numerator and denominator are the same, then the horizontal asymptote is given by the equation y equals a sub n divided by b sub n, where a sub n is the leading coefficient of the numerator and b sub n is the leading coefficient of the denominator. Now, there is a mistake here. That should just say a sub n. There's a couple extra letters there, so please disregard that. It should just say a sub n. Now, the third case is if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. So, that was a lot of information to digest. Let's look at this next rational function. We are asked to graph y equals 12x minus 4 divided by 3x plus 2. First things first, let's figure out if there are any asymptotes. So, for the horizontal asymptote, they're always going to be of the form, if there is one, they're always going to be of the form y equals and then some number. Now, this is a scenario or case, an example of case number 2, where the degree of the numerator and the denominator are the same, because both in the numerator and the denominator we are dealing with a linear function, and so both the degree of the numerator and the denominator are 1, and so in that scenario our horizontal asymptote is given by y equals, and then we take the leading coefficients. So the leading coefficient of the numerator is 12, and the leading coefficient of the denominator is 3, which if I simplify that is 4. So overall, our horizontal asymptote is y equals 4. Okay, now our vertical asymptote occurs when the denominator is equal to 0. So what we can do is we can just set our denominator equal to 0 and solve for when that happens. So we have 3x plus 2 equals 0, and I'm going to subtract 2 on both sides. So we get 3x equals negative 2, and then I'll divide both sides by 3, so we get x equals negative 2/3. Okay, so now that we have that information, that's going to be helpful for us to graph our function. Now let me just draw in my x and y axis. So that's my y-axis, this is my x-axis, and now I'm going to enter in my asymptotes. So there is a horizontal asymptote at y equals 4, and there is a vertical asymptote at x equals negative 2/3, and that's pretty close to the y-axis, so that's about here. Okay. One other thing is to see, it would be helpful to see is if there are any x and or y-intercepts. So let's start with the y-intercept. I'm going to plug in 0 into our equation and see what happens. So if I simplify that, we would get negative 4 over 2, which is equal to negative 2. So our y-intercept is an ordered pair, so it's going to be the ordered pair 0, negative 2. So let me plot that. That is right there. Okay, so now let's see if there is an x-intercept. What we want to do is we want to set y equal to 0. So we're going to have 0 equals 12x minus 4 divided by 3x plus 2. And I'm trying to solve for x in this scenario. So if I multiplied both sides by 3x plus 2, then I would get 0 equals 12x minus 4. And now I can just solve this linear equation. So if I divide both sides by 12 now, I would simplify that, and we get x equals 1/3. So our x-intercept is going to be 1/3, comma 0. So let me plot that now, which is about right here. Okay, and I'm going to leave it to you to plug in some more points to kind of get the general gist of what the graph looks like, but I have been graphing these long enough to know that our graph is going to look something like that. Okay, so that's how you graph this rational function.